SwayamPrabha. Digital India. Educated India.
Hello everybody and welcome back to this series of lecture on elements of solar energy conversion. We are here at lecture number 25. So, we have, in terms of the solar conversion devices, we have covered the flat plate collector, its different configuration variations. Then we have started looking at the concentrating collectors, and after giving the background of why concentration is required, what is the limit of maximum concentration possible for 2-dimensional as well as 3-dimensional concentration device. Now we have started the first major concentrating collector, which is the parabolic trough collector, which is a linear concentrator, and we have seen how to look at the optical properties of that concentrator. So, I will complete that discussion which we started in the last class. Here we have seen that the image that happens in the focal plane, okay, is somewhat distributed depending on the symmetry of the parabola, and the intensity is again not everywhere equal. So, all these things we have looked at, and we started talking about different kinds of solar collectors or the heat collectors, the receiver part, where we have looked at plate, we have looked at tube, and we can also have semicircular tube. Okay. So, how to determine the dimension of the receiver which will have the maximum intercept factor. That means, all the reflected rays that are coming from the parabolic dish or parabolic trough, that should intersect with the receiver part. So, let us look at that. Okay, so, first, what are the underlying assumptions? First one is that the reflector is symmetrical, because that will tell from one side how the rays will be reflected to the other. So, if it is symmetric, half of it, if we can analyze, it will be just the mirror image of the other half. And we also assume that it is a perfect reflector. In real life, your reflector will have some surface defects and it will not be exactly parabolic, and that is how you will have some defects in the image as well. But here we are assuming it is a perfect reflector. And the second assumption is that the incident rays are perfectly normal or perpendicular to the aperture plane. When is this assumption true? When we have a tracking system which is perfect. So, this means the tracking is perfect. Okay. So, basically if you have this parabolic trough and this is our aperture plane, right, and what we are assuming that all the rays are perfectly normal to this aperture plane. Okay. And when it is possible? When the parabola can orient itself exactly looking at the sun, and then only this assumption will be true. Okay. Now, under this assumption, what we can observe that the width of the solar image on the focal plane increases with the rim angle, right. So, basically if you have this parabola, so rim angle means what? The angle that the rim point makes, this is phi r. So, rim angle if increases, that means the size of the parabola increases, that also mean the image size, the width of the image will increase. Okay. So, if we look at the focal plane where this is the focal point, so we can say that from any side the reflected ray will make a cone that we have seen. In one side it will intersect shorter distance and the other side it will intersect larger distance, right. And what we can do here, we can see what are the angles. Okay. So, if you draw a perpendicular from the focal point to the one edge of the cone, okay, and so let us say that this is a perpendicular we are dropping. So, this angle, let me just remove these two symbols. Okay. Yeah. So, now this angle you can see to it, and you can find that it will be phi r minus the half cone angle, which is 0.267 degrees. Okay. Similarly, if we drop one perpendicular on the other edge of the beam, okay, so if this is the perpendicular, then this angle also you can find out, and this angle will be phi r plus the half cone angle, which is 0.267 degrees. Okay. So, these two we can find, and we can also see that if we put a, so if we have a cylindrical receiver and we want that the intercept factor gamma is equal to 1. That means, all rays intersect the receiver plane. Okay, if we want that, then what should be the minimum dia of the receiver tube? So, that is a legitimate question to ask, right. We want to know the dimension of the tube, so that all the rays are intersected. Okay. So, now again if we look at, then from one side we have this cone, okay, and you can see that if you have a, this is the perpendicular. Okay. So, if you have a tube with this diameter, Okay. So, this is the receiver tube with radius of this. So, let us say this point is, the focal point is A and this perpendicular point is C. So, a receiver tube with radius AC will intersect all the reflected rays. Okay. From one end, so this is from the right end, right, from right side end of the parabolic reflector. Okay. So, from one end you see that this C point is the limit, and the other edge, which is this edge will anyway intersect in the other part of the tube, okay, which is above. So, this edge intersect tube above the focal plane. Okay. So, that is how. So, minimum radius that you need is AC, and from the other side also you will see, from other side, that means from this side, the cone that you will find, it will intersect this particular receiver tube completely. Okay. Now, so the task is, what is AC, that we want to know, right, that will tell us the receiver tube geometry. So, now what we can write, this AC, let us say, if we, what is the origin from where this is getting reflected, let us say this point is B. Okay. So, AC, and you can join it with one point AC. So, this ACB is right angle triangle, where the angle ACB is the right angle. Okay. So, now if we want to know what is AC, that is nothing but AB sine of this half angle, which is 0.267 degree. Okay. And AB is what? AB is the rim radius of the parabolic reflector, where this RR is the rim radius of the parabolic reflector. Okay. So, basically D of this receiver will be twice of this minimum radius, which is AC, that means 2 RR sine 0.267 degree. Okay. So, that is the minimum radius that we have to use for the receiver diameter, or minimum diameter that we have to use for the receiver tube is twice RR, that means the rim radius multiplied by sine of the half angle 0.267 degrees. Okay. And we can also write from the same figure that RR is nothing but aperture, half aperture length divided by sine of phi r, that means the rim angle. Okay. So, this you have seen earlier. Okay. In the last class we have derived that. So, basically dr you can write in terms of A sine 0.267 degrees divided by sine of phi r. okay, in terms of the aperture half or aperture area, aperture width and the rim angle, you can write the minimum diameter that you require for the receiver tube. Okay. Now, next question is, if we have a surface or rather a flat surface as the receiver in the focal plane. Okay. So, if we have that, then what we can see that, okay, so if this is our receiver plane and we have the cone just like this, then what we need to have for complete intercept, we need a surface with width equal to the longer side of the image cone. Okay, that means if so, this is the longer side, right. So, if we have receiver of width of this longer side, then from one end you will have interception here and for the other end you will have the interception here, right. So, the other end interception will be at this edge. Okay. So, basically if we have the longer side width, that means it will cover the complete range. Okay. So, what is that? What is the width that we need to find, right? So, let us go back to the geometry again. So, you can say that earlier we have seen that, okay, this is the longer side and this point we said A, and we have dropped a perpendicular here at point C. Now, if we say the longer side width is EA, so longer side width is equal to EA, and that is what we want to know. Okay. And that is half width, right. So, if W is the width of the receiver plate, okay, in that case we can write W by 2, we need it to be EA, and that is AC divided by cos of this angle EAC, okay, this particular angle. Okay. And you have seen that AC is RR into sine of 0.267 degrees, and EAC also we have seen couple of pages ago. Yeah, here this angle is phi r plus 0.267 degrees. Okay. So, here this will be cos of phi r plus 0.267 degrees. Okay, clear? So, what we can write, this W will be 2 RR sine 0.267 degrees divided by cos of phi r plus 0.267 degrees, and it is equivalently can be written in terms of the aperture width A divided by sine phi r into cos of phi r plus 0.267 degrees. Okay. And that is the that is the minimum width required for a flat plate having an intercept factor equal to 1. Okay. So, these are two most common geometries, a tube geometry or a flat geometry. Another possible geometry is the semicircular cross section of the receiver tube. Okay. There also we need to know what would be the minimum radius. So, what is the minimum radius for intercept factor equal to 1? Okay. So, here what is happening? Okay. Here suppose we have this cone. Now, for the circular one we have taken that this will be the radius of the tube, because this is actually giving you intersection here and the other one is getting intercepted somewhere above the focal plane. But in this case for semicircular one, the above portion or rather the portion above the focal plane does not exist, isn't it? So, what we need to have that the minimum radius would be the shorter side, which will anyway intersect the longer side edge of the cone. Okay. So, here the semicircular tube must have a minimum radius of the shorter side of the cone intercept. Okay. That means the minimum radius would be this length, this would be the minimum radius. Okay. So, now we can find what is the minimum, that particular length we can find, and similar way we can find what would be the minimum diameter for the semicircular tube. Okay. Now, here I want you to note that even though, let me write it so that it is in front of you, which is a very important parameter. So, I would insist that you please imagine the situation, okay, because this is a two dimensional collector, okay, but the ray that is coming, that is in the form of a cone, which is a three dimensional geometry, right. So, even though the reflector is a 2D section, each reflected beam is a 3D cone, right. Any beam that is falling on the reflector and then getting reflected to the receiver, it is a 3D cone, right. So, in the perpendicular direction, that means if this is the parabolic trough, this is the receiver. Okay. So, the perpendicular plane or perpendicular direction that is going inside the board. So, that means the direction inside the board, okay, which we often designate in this fashion. So, in that perpendicular direction there will be certain width of the image, right. The image is not just a line, okay. Image is not a line on the focal plane, but it is a 3 dimension with some spread in the z direction. Okay. So, the intersection cone, intersection of the image cone from any arbitrary point on the reflector, okay, having a radius r, okay, with the focal plane would be an ellipse, okay. It is not a line, it is not a circle, but an ellipse, okay. So, for that ellipse it can be shown, I am not going into detail, but the minor axis will be 2r sine of 0.267 degrees and the major axis would be r of sine 0.267 degree divided by cos of phi minus 0.76 degree minus r sine 0.267 degree divided by cos of phi plus 0.267 degrees. Okay. So, every point on the reflector will make image of in the form of ellipse on the focal plane, and all these different images will be superimposed to give you the overall image for the 2-dimensional parabolic trough. So, that completes the optical portion of the analysis of the parabolic trough. We have seen how the images will be formed on the focal plane or different kinds of receiver geometry, what would be the minimum radius for that for complete interception. So, all those things we covered. Now what we are going to see now is the thermal analysis of a parabolic trough. Okay. We will see that there will be some similarities with what we have done for flat plate collector, and there will be some significant dissimilarity which we need to note specially. Okay. Now, let us have this kind of parabolic geometry. Of course, this is symmetric, this is the axis of symmetry, which is also the focal direction, and somewhere here we will have the receiver tube. Okay. Now, so far we have not considered anything related to the cover of the receiver tube. If you have a naked tube, then the losses will be so high because it is a concentrating collector, right. So, losses will be higher because of higher temperature. So, similar to the flat plate collector, what we have? We have a transparent cover. So, let us say that this is the transparent cover, which will also be another tube, which will be a concentric tube. Okay. And let us say, let me just say that this is the receiver tube and the top one is the transparent cover, which is also a concentric tube. Okay. Tube is the most common geometry of the receiver, that is what we are going to analyze that. Okay. Now, let us say that so from this center, this angle is nothing but our rim angle phi r. Okay. So, as the assumption is still valid that the aperture plane is perpendicular to the sun ray direction. So, any plane that is coming perpendicular to this plane will be reflected to this tube. Okay. And let us say this is the width of the aperture, which is W. Okay. Now, you can see that if we zoom this part, okay, this is the tube and then this is the transparent cover, and let us say that the diameter of this one, diameter of the receiver tube is d naught. Okay. Now, what we can say that the effective aperture area is now W minus d naught multiplied by L, right, because d naught is this portion, it is opaque, right. If it is opaque, any radiation will not pass through that region to reach the reflector. Okay. So, the effective aperture area is not W into L, L is the length in perpendicular direction, perpendicular to the board, right. So, it is not W into L, but W minus d naught into L. Okay. And the receiver area is what? That is pi into d naught into L, right. Pi d naught is the radius, the circumference of this receiver tube, and you multiply that with L in the perpendicular direction. Okay. So, now if we, the first thing for any optical concentrating geometry, if we want what is the concentration ratio, that is nothing but this effective absorber area divided by this pi d naught L, the receiver area, right, that we have seen. Basically, this is AA by AR, that means this is W minus d naught divided by pi d naught. Okay. For our tube geometry of the receiver, we have the concentration ratio, which is W minus d naught divided by pi d naught. Now, what we can write is the differential useful heat gain rate, okay, or dQu dot. What is that? Why we call differential? If we look at the tube, the receiver tube, at one small portion of it of length dx, what we can have, that we have some temperature Tf coming in some increased temperature Tf plus dTf going out. Okay. So, for that what would be the dQu? That is what our question is. Okay. So, that will be the balance of heat which is coming in from the solar radiation and subtracted, the subtraction has to be of the factor the loss that is going out to the ambient. Okay. So, this dQu dot, this will be, let me write this expression first, then I can explain. Tp minus Ta, this whole thing multiplied by dx. Okay. So, what are the terms here? So, first term, if we look at, this is the heat, the amount of radiative energy reaching through the reflector. So, if you see, let me just compartmentalize these things. This is the total amount of radiation coming in terms of beam, okay, not as diffuse, because concentrating collector beam radiation is the major one. So, diffuse one we can completely neglect. So, IB RB is nothing but, RB is the ratio between the tilted plane intensity to that of horizontal plane intensity, right. So, IB RB is giving you what is on the aperture plane, what is the intensity of the solar radiation, and then the next part is the width of the aperture. Okay. So, that is the effective width is W minus D naught. So, that is the total amount. Now, what is rho? Rho is the reflectivity of the parabolic reflector. Now, all the rays that are falling on the parabolic reflector, a portion of it will reach to the reflector, right, because reflectivity is not 100%. Whatever coating you use, whatever material you use, the reflectivity will be less than 100%. That means rho will be less than 1. Okay. And then what is this? This is the intercept factor. Let me write this. This is the reflectivity of the parabolic surface. Okay. And then this gamma is the intercept factor. So, it will tell how much of the reflected beam will be intercepted by the receiver tube. Okay. And what is this? This you know, this is for the effective transmissivity absorptivity product for that system of receiver tube and the transparent cover, okay, and that also for beam radiation. So, that is why this whole first term is giving you amount of radiative energy reaching through the reflector. Now, what is the second term? Second term is nothing but the amount of radiative energy reaching to the receiver directly. That means, if we look back at the geometry, you can see that here some rays from this direction, some rays will reach the receiver directly, right. It will not be reflected through the parabolic surface, but will reach it directly. Okay. So, this is the part, the direct portion of it, and here again what we see that IB RB will be there, which is the tilted surface intensity, and then d naught is the width of that particular receiver tube, right. So, that is why d naught, and then again the tau alpha b, which is the effective transmissivity absorptivity product. Okay. So, that is the direct portion. So, first and second term gives you the total input, and the third term is giving you the loss part. So, you can see that this loss coefficient is there, you have the circumference pi d naught and then the temperature difference. So, this is basically the area, the loss coefficient, and this is the delta T part, right. So, that gives you what is the effective loss from the receiver tube. Okay. Now, usually for flat plate collector we have seen that we use the absorbed radiation in terms of S, right, that is the common symbol that we use. So, if we write the expression of dQ dot in terms of S, then what we can write? The S into the effective aperture width will be equal to this IBRB multiplied by W minus D naught rho gamma tau alpha b plus this IBRB multiplied by tau alpha b into pi d naught, right. So, this is the first two terms in the expression of dQ dot, okay, and that is the input which is coming, and we can write it in terms of S into the effective aperture width. So, basically S you can find out to be IBRB rho gamma tau alpha b plus IBRB tau alpha b multiplied by d naught W minus d naught. Sorry, this expression will be not pi d naught, but d naught. Okay. Yes, that is correct. Okay. So, now the equation of dQ u naught is simplified in terms of S minus UL divided by C Tp minus Ta right. Here we have introduced C. C is nothing but, you have seen that C is your W minus D naught by pi D naught. Okay. So, C is W minus D naught by pi D naught. Okay. So, everything else is same, I just replaced that complicated expression in terms of S, which is the absorbed radiation per unit area, and we have introduced the concentration ratio, which is C. Now, similarly the dQ naught can be written in terms of the heat transfer rate from the tube or receiver tube to the fluid, right. That we can do in terms of this, and we can also do in terms of heat carried by the working fluid. Everything will be dQ naught dot, right. So, dQ u naught dot is equal to Hf into pi di dp minus Tp minus Tf multiplied by dx, right. So, here this is the inner diameter of the tube, this is the heat transfer coefficient for the fluid inside the tube. Okay. And the same thing we can write in terms of the increase in temperature of the fluid flow. So, m dot Cp dTf, that also we can write. Okay. So, now if we use the same expression, this expression of dq naught and this particular expression of dq naught, what we can write, that dq u naught is equal to f prime s minus ul by c Tf minus Ta. Now, not Tp minus Ta, but Tf minus Ta multiplied by W minus d naught dx. Okay. So, F is again the collector efficiency factor, okay, and F you can write as 1 over UL multiplied by 1 over UL divide plus d naught by di multiplied by Hf. Okay. So, here you note that we have a cylindrical geometry, right, cylindrical tube, and that is why this factor d naught by di is coming, okay, is coming. This you have noted from the conduction radiation conduction knowledge, okay, and for thin tube this is basically d naught by di is equal to 1. Okay. For thin tube you do not have any difference between the outer and inner diameter. Okay. Now, in terms of the fluid temperature increase with the length dTf dx, you can write. So, here the procedure is very similar to what we did for flat plate collector. So, I am not going into detail of every bit of equations from where it is coming everything, but the major equations that you are going to get, I am going through that steps. Okay. So, this will be f prime pi d naught ul divided by m dot Cp multiplied by Cs, which is concentration ratio multiplied by the absorbed radiation per aperture unit width divided by ul minus Tf minus Ta. Okay. Similar equation we also got for flat plate collector. Now, if we solve the equation with the boundary condition that Tf equal to Tf inlet for x equal to 0. Okay. If you solve that, what you will get, Cs by ul plus Ta minus Tf divided by Cs by ul plus Ta minus Tfi will be equal to exponential negative of f prime pi d naught ul x m dot Cp. Okay. So, this is the solution which will tell you how the fluid temperature will increase from the inlet towards the outlet. Okay. So, for the total heat gain, okay, this x equal to L and we have Tf equal to Tf naught. So, what we can write from the above equation, we will have Tf naught minus Tfi divided by Cs by ul plus Ta minus Tfi is equal to 1 minus exponential the same expression f prime pi d naught ul. Now you have L, capital L, because x is equal to L, and divided by mCp. Okay. So, this expression tells you what would be the overall temperature rise of the working fluid as it passes through the receiver tube. Okay. So, what we can write? We can now integrate this, and we can write mCp Tf naught minus, that would be the total useful heat gain rate, and this will be m dot Cp and Cs divided by UL plus Ta minus Tfi. I am just substituting that expression, exponential of minus f prime pi d naught UL L divided by m dot Cp. Okay. And the same thing we also have seen that we can write in terms of the heat removal factor Fr, W minus d naught multiplied by S multiplied by S minus UL by C Tfi minus Ta. Okay. Where Fr is our heat removal factor. So, in each step you should draw parallel to the analysis that we have done for the flat plate collector. That will help you understand the physical meaning of each of these terms. Okay. This is nothing but m dot Cp pi d naught L UL multiplied by 1 minus exponential minus of f prime pi d naught UL L divided by m dot Cp. Okay. So, that completes the analysis, and what you can find? You can find the effective efficiency of the collector. Efficiency means what? What you are getting out at the cost of the input. Okay. So, output by input is your efficiency. So, you can write Ni is equal to Qu, okay, divided by this Rb Ib Wl. Okay. So, this is the output. I should say dot because this is a rate, and this is the total input to the aperture in terms of solar radiation. Okay. That is how the efficiency of a parabolic trough collector is computed. So, that completes the thermal analysis, but we will need to discuss few things, how to find this UL and other things, which we will complete in the next class. Here we stop for this class. Thank you for your attention.